Welcome back to Feedback Control Systems. This is Module 4.5. We're going to talk about nonlinearity's impact upon the time response. The objectives of today's module are to look at a saturation example, a dead zone example, and then finally a backlash example. These are the three nonlinearities we described back in modules 2.4 or so, and we want to look at what impact some of our time responses may have from these three cases. First of all, the saturation example. Back in the previous module, we showed this characteristic, and we actually looked at the impact of, there's a linear region here to the side. There's a linear region in this region here, and then there's a nonlinear region to the right of that. So we refer to that as amplifier saturation. And one of the things we want to do is using Simulink graphically here. Well, let's do a step input of 10 volts, so 0 to 10 volts here. And in our system here, we want to do two things. We first want to say, well, what's the impact here? Let's look at this branch right here. And we have our transfer characteristic of a very simple first-order transfer function representing our motor, load, gears, etc. It's a first-order transfer function, and we're going to look at that on a scope. And what you'll see is without saturation, based on our characteristics here, we can actually go in and look at the response relative to that. And next, what I want to do is so that's our without saturation. Now we also have a curve with saturation, and that's this block that I'm showing here in red. Well, maybe even though we have 10 volts available to us, maybe we for some reason want to limit the amplifier we bought may be limited to, say, plus or minus 5 volts. So even though we're trying to say, hey, give us 10, the amplifier only has 5 volts to give. And so when we put that onto our response here, notice that we have the same transfer characteristic. We just want to compare the two, and the thing that we are going to look at in this case is the variable of angular velocity. So we're looking at angular velocity as a function of time, and we can see the two responses. So the quick thing is when we don't have saturation, when our amplifier is not limited in terms of how much voltage it can apply, what we'll see with the characteristic is we'll get a steady state value of this velocity, the speed, if you will. And however, if we are limited, if the amplifier cannot achieve our command, it's going to give us something less. Then what happens is we're not going to go as fast as we think we are. And so that's very important to know. Even though you command something to go a certain speed, if you're not getting that, that's going to be very important to know in your application. So in Simulink, what we can do is they have blocks where literally it's called a saturation block, and we can go in and change the parameters and vary and look at the impact. So that's a saturation example. The next example we want to do is that dead zone example. So from a previous module, we saw this characteristic. And again, what we said is given some input, the motor may actually not respond until a certain amount of time. So for example, until the motor terminals have a certain voltage threshold that's reached, the motor is not going to move, either due to some friction in the brushes or bearings or some other thing. And we refer to that as our motor dead zone. So just like before, we are going to have an input. This time we're going to use a sinusoidal input in Simulink, and it has an amplitude and frequency as you see there. And again, we're going to compare two paths. We're going to say, here's a path with no dead zone, same motor gear load transfer function we used on the previous slide. And then remember the previous slide, what we did is we looked at what was the angular velocity, but now I want to look at angular displacement or position. Well, the difference between velocity and position it would be I'd have to integrate velocity to get that angular position or displacement. And that's what I would see without any dead zone here in black. Or I could put in this block referred to dead zone and basically have this characteristic from, in this case, -2 to 2, and it's going to apply itself to the same transfer characteristic and integrator, and we'll see in blue down below with the dead zone what's going to happen. So what we'll see is our output displacement isn't going where we want it to go due to that dead zone. Okay, so that's very important to know, again, relative to what our goals in the system is. We may think, we're giving it this input, this frequency, this amplitude, etc. And if the output is not actually doing what we think due to some of the dynamics, and again, we're modeling this. Let's say our system did not model this, and we're thinking ahead. We're thinking, I don't need to model backlash or dead zone or saturation. Then what you'd see here, your prediction would be here in black. But then you get into the lab, and then physically, if you have that dead zone or that backlash or something else, you would see the response shown in blue, and you'd be like, wait a minute, that's supposed to go to 1.1, 1.15, but it's only going up to like 0.5 here. There's a big difference in what I'm seeing and what's wrong. It's usually that something wasn't modeled appropriately or correctly. Not always, but that could be the culprit that you can run into. And finally, we're going to look at backlash. So this is a system that had gears. So again, our same motor, load, gear, transfer characteristic. Again, similarly looking at angular displacement. Same sinusoidal source that we had before. And now when we look at backlash relative to the gears, notice the location. Previously for the saturation and the case we saw before with the dead zone, that was modeled to the left of the motor gear. But because that backlash has to do with that gear position, notice it's modeling on the output after we have that position as shown here. So again, whether we have backlash, the lower path right here, we do not have the backlash. That's the waveform that we see here in black. Or if we do have the backlash integrated into our model, what we'll see is that sort of saturation. Backlash deadband width is 0.15. Okay, so that's kind of what we're seeing right there. You'll see that limit relative to the 0.15. So again, if we're modeling something and if we don't model with the backlash in our simulation and say, okay, we're going to go in this range here, but in the lab, wait a minute, it's going a little bit smaller, and then you'll have to kind of figure out, trace down why you're seeing this in the lab and why your model didn't predict it. Hopefully then you go back and fix your model to incorporate that, because you want a model that actually can interpret and predict what you're actually going to see in the lab. Sometimes this is an iterative process, and as we go through some of our examples, we'll see when we should include it or when we are safe to ignore. So that will conclude this module. If you have any questions on this material, please don't hesitate to reach out. Thank you.